So what we're going to do now is we're going to start with surface integrals, and we're going to start out by talking about finding surface areas. So let's suppose that we have a parametrization of our surface area, our surface, and we've got r of uv. Okay, we've got r of uv, and we'll imagine that we've got this surface in 3 dimensions, and just a generalized surface, something that looks like this. Okay, whatever. And what I'm going to do is I'm actually going to go in here, and I'm going to break this up into a gridded region. Okay, so we're going to imagine that I've got this as a gridded region, and we're going to be integrating. And so what you can imagine, like what we've been doing, anytime you're doing any kind of calculus, you really want to start looking at just a generalized value for this particular gridded region. So like, let's say, for example, I go into the gridded region, and I've got, right, here's I'm going to zoom out one of those regions into here, okay? And what I want to do is I want to find the generalized area of that particular surface. Because what I'm going to do is I'm going to say, okay, so here's an equation for the area of this general region. Then I'm going to make it very, very, very small. And then I'm going to add up all of those areas, and that will give me the area for the surface. Okay? That'll give me the area for the surface. By the way, my surface is going to be called S. Okay? That's the process of integration. We've been doing that throughout. And so now we want to think to ourselves, okay, got it. All right. How do I go about finding the area then of this little region right here? Okay. Now, the first thing that you want to get is that the location here is really not going to make that much of a difference, like where it's actually located. All that's going to matter is the dimensions. We just basically want to know, essentially, how long this side is and how long this side is, and we multiply the two of those together, and we end up giving ourselves the area of that region. But it's really not quite that simple. What we're going to do is we're going to look for an approximation for that region, okay? And so the approximation for that region is going to be a plane. So we've got our region, right? Okay, let's imagine that it's kind of on a slanted surface. There's our region, and we're going to imagine that we get a tangent plane, okay? And if that tangent plane, if the region is small enough, that tangent plane should give us a pretty darn great approximation, okay? So we've got this little tangent plane, all right? And so in order to find the equation for the tangent plane, we're going to need the normal, okay? We're going to need to find the normal. We got this n, that normal vector, and that normal vector is going to define the plane. It's going to define everything about the plane except for its location in space, okay? Which is great because basically if I could find the magnitude of the normal, that's going to equal the area of the tangent plane. And that's going to end up being an approximation, so it's going to be approximately equal to the area of my surface part. So that's kind of like what we're dealing with here. We're going like, okay, I've got to go find the area of this little region. How am I going to go do that? Okay, I'll find the normal, and then I'll take the magnitude of the normal, and then that's going to give me an approximation, okay? An approximation of that surface. Make the surface small enough, add them all together, and I end up getting the area of the entire surface. So how do I find the normal? Well, what I'm going to need is I'm going to need a vector. I'm going to need 2 vectors on that plane. Okay, so I'm going to need 2 vectors on that plane, okay, to help define that portion of the plane. And so what I'm going to do is I'm going to actually find the tangent vectors, the directional derivatives, okay, the directional derivative or the tangent vectors, directional derivative in the u, and the directional derivative in the v. Okay, so essentially what that's going to look like is that's going to look like if we've got r of uv, okay, then I'm going to take, I'm going to multiply the length of this vector, right, and we'll call that delta u, for example, and I'm going to multiply that by t of u, okay, and then I'm going to take the length, delta v, okay, and I'm going to multiply that by t of v, and tv here, okay, which is like the tangent vector in the direction of v. And then I'm going to take the cross product of the two of those. That's going to end up giving me the normal, okay? So let's define this T of V and T of U, okay? So T of V is going to end up equaling R vector of UV, okay? And we're going to take the partial with respect to V. Okay, for UV. And so that's essentially going to end up being XV, YV, ZV. All right? And we'll evaluate it at some point. We'll talk about that in just a second. But for right now, it's going to be the partial with respect to V for RV. And then our TU, okay, which we call the tangent of U, is going to be RU of UV. So it's going to be the partial with respect to U. So it's going to be XU, YU, ZU. Okay? So what we'll do is we'll evaluate. We're going to take TV at some point. Okay? We'll call it UI VJ. So that's some point. And then we'll have TU at UI VJ as well. Okay? And that'll give us our tangent vectors. So now what I'm going to do is I'm going to say, okay, well, the normal vector, this normal vector here, is going to define the plane, the tangent plane, to the surface at that point. Now that tangent plane is infinite, so we're going to deal with that in just a second. But we do just want to find that normal vector. So that normal in the region N, okay, in the region around UI VJ, okay, is going to equal then the cross product TU cross TV. All right, we've got the two tangent vectors. We take the cross product, we're going to get the normal vector. So this defines the tangent plane. Now to get our area, all we're going to need to do is we're going to need to scale the tangent plane. Okay, the scale the tangent plane. So what we're going to do is we'll multiply by delta U and delta V. Okay, so we're going to take that, we're going to find our area, or our approximation of our area, is going to be approximately equal to, it's going to be the magnitude of delta U, TU, cross delta V, TV. Okay? So this is the direction. It's like a directional derivative. Direction, this is the length. The length. Take their cross product. We end up with getting a definition for that plane, the entire plane. It's normal. So this ends up equaling delta, or excuse me, the magnitude of TU cross TV, delta U, delta V. Okay? And that's an approximation for our area around, in this case, UI VJ. In the area around UI VJ. Okay? So what I'm going to do now is I'm actually going to say, okay, well, what if I want to figure out the entire area of the surface? We've been doing this a lot inside of integration. What we'll do is we'll just summate. So our area of the surface, okay, is, and we're going to call this S, is going to equal then the sum, or it's going to be approximately equal to, excuse me, the sum I equals 1 up to n, and the sum j equals 1 up to n of TU at UI VJ cross TV at UI VJ, okay, delta U, delta V. What we do then is we're going to take the limit as n approaches infinity, so we make these smaller and smaller and smaller and smaller, and that's the sum I equals 1 up to n, the sum j equals 1 up to n, okay, of this cross product TU cross TV, or TU UI VJ cross TV UI VJ delta U delta V. And what we get is we get the integral, okay, or the double integral of TU cross TV du dv. Or dA, depending upon, you know, this is for rectangular, okay? if, for example, we're using polar, we would have r dr d theta. Okay, so we rewrite this. We can rewrite it as the integral, double integral tu cross tv and dA. Okay, and that's our region D. So that ends up being the equation for our surface integral. Okay, and all it is it's thinking to ourselves, okay, we're going to generate this. We're going to have a tangent vector to our surface, right, in the u direction, a tangent vector in the v direction. Okay, we take its normal, and then we take the magnitude of that normal, essentially. We sum those all up, okay, and that gives me the surface area of this region. By the way, this thing right here is going to be called ds. And that's d big S, and the S stands for surface area, and it'll end up equaling the magnitude of tu cross tv dA. Okay? And so we're going to be seeing that a lot more later. So to define our surface integral, we're going to let r uv equal to x uv, y uv, z uv with a parameter domain D, and it's a smooth parametrization of surface S. Furthermore, we assume that S is traced out only once. One of those ones, a lot like the line integral one. So the surface area of S is going to be the double integral of D, tu cross tv dA, where tu is the partials with respect to u, and tv is the partials with respect with v for our parametrization. All right, so now let's find the surface area of a surface with parametrization r uv equal to u plus v, u squared 2v, u greater than or equal to 0, less than or equal to 3, and v less than or greater than or equal to 0, less than or equal to 2. So what I'm going to do is I'm going to remember that my surface integral is going to be the integral over d of tu cross tv, its magnitude, and then we're going to have, in this case, it'll be du dv, because it's dA, and this is in rectangular. So what I'm going to do first is I'm going to first find tu. So tu is going to be the derivative with respect to u of r. So that's going to end up being 1, 2u, 0. And then tv is going to be the derivative with respect to v. So it's that the partial with respect to v. And it's going to be 1, 0, 2. Then what I'm going to do is I'm going to take their cross product. Okay, so this is going to be 1, 2u, 0, 1, 0, 2. So I'm going to have 2u times 2 minus 0. So 2u times 2 minus 2 minus 0. So minus 2. And then those two. So plus 0 minus 2u. And this ends up equaling 4u minus 2u minus 2. So this is 4u minus, or excuse me, 2u minus 2. We'll take the cross product. So this is going to end up being 2u times 2, so that's 4ui plus, or excuse me, minus, and then 1 times 2 minus 1 times 0, so this is going to be 2j plus, and then this is going to be 1 times 0 is 0 minus 2u k. Okay? Its magnitude then, because we need to find the magnitude of tu cross tv. So here's tu cross tv. Magnitude tu cross tv ends up equaling the square root of 4u squared plus negative 2 squared plus negative 2u squared. And this ends up equaling the square root of 16u squared plus 4u squared. So this is equal to 20u squared plus 4. Take the square root of that. And so that'll end up being 2 times the square root of 5u squared plus 2. Excuse me, plus 1. I'm going to use that now, set up my surface integral, or excuse me, my surface area integral. So this is going to then be, we'll take it 0 to 3, and then 0 to 2. Okay, we'll do our u's first, and this will be 2 times the square root of 5u squared plus 1, evaluated from, we've got du, dv. And then basically you'd use a trig substitution here. And that's going to end up being approximately 43.02124, accounting for some rounding. Okay. Essentially, you've got a trig substitution there, or you can actually notice that this is basically an arctan. Yeah, so there you are. Big thing to notice here, we took the partials with respect to u for our parametrization, our partials with respect to v of our parametrization. Okay. Then we took the cross product of those, took its magnitude, okay, and then that's what we integrated over, all right, with our balance being the balance for our parametrization. All right, and that's how you find the surface area. Let's suppose now that we want to find the surface area of a sphere with radius r. So what we're going to do is we're going to start out with, one, it's a sphere. So I'm going to be parametrizing using spherical. Also, you might already know what the surface area of a sphere with radius r is. Great. Compare it against what we've got. So what we're going to do is we're going to say, okay, so the equation, the rectangular equation is x squared plus y squared plus z squared is equal to r squared. Okay, that's the equation for a sphere. And in this case, we know that x, because we're going to use spherical, is going to end up being equal to r cosine theta sine phi. Y is going to end up equaling r sine theta sine phi. And z ends up equaling r cosine phi. Okay? And what we're going to have, since it's an entire sphere, we're going to actually have our parameters be phi and theta. Theta is going to be going from less than or equal to 0, less than 2 pi. And phi is going to go from 0, greater than or equal to 0, less than or equal to pi. Okay, and those are going to be the values for our parameters. So my parametrization, we're going to call this r of theta phi, okay, is going to equal r cosine theta, and this is r the vector, by the way, r cosine theta sine phi, r sine theta sine phi, and r cosine phi. Okay, so we're going to need to find t theta cross t phi. Okay, and we'll find its magnitude. Remember, that's going to be the part of the work that we're going to need to do. So what we'll do then is we're going to calculate t theta. So t theta is going to be then r, and this will be actually negative r sine theta sine phi. And then we're going to have r cosine theta sine phi. And then 0. Okay, because no theta is in r cosine phi. Then we'll have t phi, and t phi is going to end up being r cosine theta cosine phi. Then we're going to have r sine theta cosine phi. And then we'll have negative r sine phi for our z value. Okay, and that's t theta and t phi. Now we're going to need to find the cross product of those two. So we've got t theta cross t phi, and that'll end up equaling negative r sine theta sine phi, r cosine theta sine phi, and 0. And then r cosine theta cosine phi, r sine theta cosine phi, and negative r sine phi. Take the cross product of those three, and we end up with, we'll start here, we're going to get negative r squared cosine theta sine squared phi. Okay. I plus, we'll get r squared sine theta sine squared phi j. Pardon me, that should be a minus. Minus r squared sine theta sine phi j. plus, and then negative r squared sine squared theta sine phi cosine phi minus r squared cosine squared theta sine phi cosine phi. Doing a little bit of algebra, or maybe a lot of algebra, depending upon how you look at it. We'll get negative r squared cosine theta sine squared phi. Our first component. Second component is going to be negative r squared sine theta sine squared phi. Okay, and then our third one, we could pull out. Notice that we've got the sine squared and the cosine squared. We could pull out a negative r squared sine phi cosine phi. So this ends up being negative r squared sine phi cosine phi, and then notice that it would be multiplied by sine squared theta plus cosine squared theta, which would end up just becoming a 1. Now we just got to find the magnitude of this. So the magnitude of TU cross TV is going to equal, it'll be the square root, okay, and this is going to be negative r squared cosine theta sine squared phi plus negative r squared sine theta sine squared phi squared, both those squared, plus negative r squared sine phi cosine phi. Okay? So this is all going to be the square root. This is going to be r to the fourth. We're going to be able to pull out an r to the fourth. Notice that I'm going to have a cosine squared theta and a sine squared theta. Okay, so they're going to be added together, and I'm going to be left with a sine squared phi. So this is going to be sine to the fourth phi, plus, and this is going to be sine squared phi cosine squared phi. Drag out a sine squared phi, you get the square root of r squared sine squared phi, and then you're left over with a sine squared phi plus cosine squared phi, which is just equal to 1. So this ends up equaling r squared and then the square root of sine squared phi. Now, the reason why we're not going to include a plus or a minus for the sine squared phi is because we want to notice that we're only looking between 0 to pi for phi. Remember, that's our domain 0 to pi, and so consequently, we don't need to actually deal with the negatives of sine. We're only going to have the positives of sine, so we can rewrite this as r squared sine phi. And that is our cross product, TU cross TV. So my integral, I'm going to have my integral is going to be from 0 to pi, and then 0 to 2 pi, and this will be r squared sine phi d, in our case, d phi d theta, and that's going to be r squared then, the double integral, 0 to 2 pi, 0 to pi, we got sine phi d theta, d phi, or excuse me, d phi d theta, and so that's going to be r squared. We'll take the first, that 0 to 2 pi, okay? And this is going to end up being negative cosine phi evaluated from 0 to pi. And this will be then d theta. This is going to be 2, okay? So we get r squared, the integral from 0 to 2 pi of 2 d theta, okay? So that's going to be 2 times 2 pi times r squared, which equals 4 pi r squared. For those of you who are thinking the surface area of a sphere is 4 pi r squared, there you are. There it is, okay? So you can see that we can actually operate using spherical coordinates as well as utilizing our rectangular ones for u and v, okay? And sometimes this actually ends up being a lot easier, especially if you're dealing with things that are spheres. Spherical coordinates are used for stuff with spheres. Let's take a look at one more example. Let's say we want to find the surface area of a cylinder that has a radius of 5 meters and a height of 12 meters. So we know that the area of the equation of a cylinder is going to end up being x squared plus y squared equals r squared. Okay, and so consequently, what we're going to do is we're going to have to go in and parametrize this. Okay, create a parameter for the surface. What we're going to do then also is that we're going to define our z in terms of our height. So z is going to go from 0 to h. Okay, and we're going to let it basically, it's going to end up being the value u. Okay, so we'll change z equal to u. And then for x squared and y squared, remember with a cylinder, how we can write this is we can write it as the radius, so 5, and then cosine, say v, and then 5 sine v, and then u. And then, like I said, we can create the height by defining the height in terms of z. So our domain here is going to end up equaling the set of all uv such that v is greater than or equal to 0, less than or equal to 2 pi, and u is greater than or equal to 0 and less than or equal to 12. Okay, so basically we're going to go from 0 to 12 in terms of our height. Okay, and our angles here, v, are going to be in terms of 0 to 2 pi. So what I'm going to need to do now is I'm going to have to find tu. So tu is going to end up equaling 0, 0, 1. And then tv is going to end up equaling negative 5 sine v, 5 cosine v, and 0. We'll take their dot product, or excuse me, their cross product. So I've got 0, 0, 1. I got negative 5 sine v, 5 cosine v, and 0. This ends up equaling, okay, negative 5 cosine v I plus, or rather minus, every time, minus negative 5 sine v j plus, and we're going to end up with 0 k. Take its magnitude, so the magnitude of tu cross tv is going to end up equaling the square root of, and this will be negative 5 cosine v squared plus negative 5 sine v squared plus 0 squared. And that, notice that this is going to be cosine squared v and sine squared v. That's going to end up equaling the square root of 25, which is just going to end up equaling 5. Which makes a lot of sense, right? Okay, because you're looking basically at the area of the tangent plane for the entire space, so that's going to end up being 5. So now we're going to take the integral. The integral is going to go from, let's say, 0 to 12, and then 0 to 2 pi. And we're going to get 5 du dv. So 5u evaluated from 0 to 12. And then we'll have the integral from 0 to 2 pi, and that'll be dv. And so this is going to end up being 60 times the integral u 0 to 2 pi dv. And that ends up equaling 60 times 2 pi, which equals 120 pi. And there we go. And that's how we can find the surface area of those cylinders. This is just to kind of give you an example of how to work with surface areas. Clearly, surface areas of spheres, surface areas of cylinders, you're probably just going to want to use the equations. It's going to be a hell of a lot easier than finding a double integral, but at least this gives you some examples of how it is that we can go out and find surface areas. You're going to find also that this ds comes up a lot, right? It comes up a lot. We're going to see it a lot when we start looking at surface integrals, okay? All right, so this ends the lesson on surface area.